Good afternoon, everyone. My name is Allison Savage, and I'd like to welcome you to the Indoor Air Quality Science webinar series hosted by US EPA's Indoor Environments Division. Today's webinar, providing insights from the Indoor Exposure to Fine Particulate Matter and Practical Mitigation Approaches workshop, will be presented by Dr. Richard Corsi. Dr. Corsi is Dean of Engineering at the University of California, Davis, and served as chair of the planning committee for the workshop that we'll hear about today. Prior to his current position, Dr. Corsi spent the majority of his career as a faculty member, department chair, and endowed research chair at the University of Texas at Austin in the Department of Civil, Architectural, and Environmental Engineering. Dr. Corsi is an internationally recognized expert in the field of indoor air quality with a specific interest in physical and chemical interactions between pollutants and indoor materials. His concept for a low-cost, accessible, and effective air cleaner, the Corsi-Rosenthal box, is now being used as an open-source do-it-yourself approach worldwide for reducing exposure to the SARS-CoV-2 virus, wildfire smoke, and more. Dr. Corsi was inducted into the International Society for Indoor Air Quality and Climate's Academy of Fellows in 2008 and is immediate past president of the Academy. Before we get started, I would like to remind everyone that this webinar is being recorded and will be made available on the EPA website at a later date. I'll also take this opportunity to mention that if you'd like to download a copy of the proceedings of the workshop we'll be discussing today, you can visit the National Academies Press webpage. You can also find more information about today's topic, indoor particulate matter and related activities at the National Academies, on the EPA website. And we'll put those links in the chat box for you. Please note that today's presentation reflects the professional opinion of the speaker and does not necessarily represent the position or policy of the US EPA. If you have a question during today's presentation, you can type it in the Q&A panel on the right-hand side of your screen at any time. Questions will be read to the speaker for discussion at the end of the presentation. If you need any technical assistance, you can submit those questions through the Q&A panel as well. We look forward to hearing from you. So Rich, thank you again for speaking today. And with that, I will hand it over to you.
Yes, thank you so much, Allison. And allow me to begin with the following as a foundation before I get into the specifics of the workshop. There's overwhelming scientific evidence that exposure to outdoor fine particulate matter, or PM 2.5, is associated with a range of short-term and chronic health impacts, including asthma exacerbation, acute and chronic bronchitis, heart attacks, increased susceptibility to respiratory infections, and premature death. And the burden of these health impacts falls more heavily on underserved and marginalized communities. And that'll be a thread that you'll hear throughout the workshop findings. Indoor exposure to PM 2.5 is far less studied than outdoor exposure, but I believe deserving of more attention as a potential source of adverse health effects. And here's why. Much of the particles associated with outdoor sources are actually inhaled indoors. And so one can surmise that our inhalation of these particles indoors contributes to evidence of health effects that we see from outdoor epidemiological studies. We add a lot of particles to indoor atmospheres from sources that reside indoors. And on average, Americans are indoor creatures. We live on average to 79 years old. We spend 69 of those 79 years domiciled inside of buildings and 54 years of our life inside of our residences. So homes are a really important environment for exposure to fine particulate matter. We spend about half of those 54 years in one room in our home, in the bedroom. So the indoor, and we only spend about 6 years of our lifetime actually outdoors. So the indoor environment is important, and the workshop I will discuss today focused on indoor environments and particularly on residential and school environments. So the workshop outcomes that I'll discuss today would not have happened without the outstanding support of the National Academies. In particular, I want to thank Dr. David Butler, the J. Herbert Holloman Scholar of the National Academy of Engineering, for his tremendous support, insights, and actions on behalf of the Planning Committee. And I also want to thank the following staff of the National Academies for their support: Drs. Guru Madhavan, Kathleen Stratton, and Courtney Hill, and Mr. Michael Holzer. The National Academy of Sciences was chartered by the U.S. Congress in 1863 as an independent non-governmental institution. And part of the charter is the Academy shall, whenever called upon by any department of government, investigate, examine, experiment, and report upon any subject of science or art And that's what this workshop is about. The National Academies was called upon by the US EPA to complete this study. The series of workshop sessions that we completed were sponsored by the United States Environmental Protection Agency's Office of Radiation and Indoor Air. And I want to thank Laura Kolb of the Indoor Environments Division for providing the committee with its statement of task. And special thanks to Jonathan Edwards, who's the director of the Office of Radiation and Indoor Air, for his support of the workshop. In 2020, the US EPA's Indoor Environments Division tasked the National Academies to convene a planning committee to, and you can see the charge here, conduct a workshop on the state of the science on exposure to, and key words here, fine particulate matter, and I'll talk about what that is in just a moment, its health impacts and engineering approaches and interventions to reduce exposure risks, including practical mitigation solutions in residential settings. And the planning committee is requested to consider the key implications of scientific research and engineering practice for public health, including potential near-term opportunities for incorporating what is known into practice, and number two, where additional research will be most critical to understanding inner exposure to PM 2.5 and the effectiveness of interventions. So we're talking about particulate matter today, and the workshop focused on particulate matter. Particulate matter is a mixture of solid particles and liquid droplets found in air. Sometimes the particles are solid with liquid on them, so it's a combination of the two. And these particles originate from indoor as well as outdoor sources. So we're focusing on indoor sources today with some outdoor sources, but typical indoor sources of particulate matter include things like cooking and resuspended dust and particle emissions from candles. Can also occur as a result of chemical reactions. And within the large sphere of particulate matter, we're really focusing on what's called fine particulate matter. And fine particulate matter is fine inhalable particles with diameters of 2.5 microns and smaller. And as some context, to the right here, you can see an image that's from the US EPA of the cross-section of a human hair, which is typically about 50 to 70 microns. It might be as much as 100 microns if you have very coarse hair, right? And superimposed on this cross-section of a human hair is what's called PM10. So these are particles that would be 10 microns and smaller. And the blue beads that you can see kind of going around the human hair here are PM10. Those would be 10 micron particles. And remember that that also includes particles smaller than these. And then if you can see the little pink beads or particles that are surrounding one of the blue particles there, that would be PM 2.5. Those would be 2.5 micron particles. And remember that 2.5 micron PM 2.5 can even be smaller than these beads. So we're talking about very, very small particles that stay suspended in air. They're invisible to the human eye. And the particles that make up PM 2.5 span about 250-fold variation in size, from about 0.01 microns to 2.5 microns. But if you convert that to volume, it's about a 16 million-fold difference in volume from the largest PM 2.5 particles to the smallest. And to give you some context, that's the same ratio as we would get between an Etruscan shrew and a gray whale. And that's attributed to Bill Nazaroff, one of our speakers in our workshop. So the selection of speakers and design of the workshop topics and flow was possible because of the enthusiastic, focused, sometimes I would say exhausting efforts of many outstanding scholars and colleagues who collectively served as the planning committee. I want to acknowledge each here. I was honored to serve as the chair of the committee, but Seema Bangar of WeWork, Renji Chan of Lawrence Berkeley National Lab, Linda McCauley of Emory University, Elizabeth Matsui from the University of Texas at Austin's Dell Medical School, Kim Prather from the Scripps Institution of Oceanography at UC San Diego, David Pui from University of Minnesota, Jeff Siegel from the University of Toronto, and Marina Vance from the University of Colorado Boulder. That group, that planning committee, really spanned all of the topics that we needed to cover and helped to organize the workshop. The workshop was held over 3 sessions from April 14th on April 21st and April 28th in 2021. The sessions were attended by more than 600 participants from over 30 countries, and you can see the countries that tuned into the workshop on the map on the right, and 45 US states and the District of Columbia. The sessions were comprised of keynote presentations and roundtable discussions. We're dealing with a very complex system. And I want everybody to really realize that today, that this is not a simple system. We're talking about outdoor sources of particulate matter, particles that are emitted outdoors, penetrating into buildings. Added to those particles are particles emitted from indoor sources, shown as the green little spheres here instead of gray. Those particles move around the indoor environment. We can form particles from chemical reactions that occur inside of buildings, and I'll talk about that in a little bit. Temperature and relative humidity, environmental conditions inside of a building affect the transformation and the growth and the shrinkage of particles. Those particles can come in, it can deposit on indoor surfaces, as shown by the blue lightning bolt here near the floor. Eventually, those particles can come in the breathing zone of an occupant who inhales them, and there can be all sorts of health impacts from that. And then there's all sorts of ways we can control or reduce the levels of particles through ventilation, which actually might bring more particles in from outdoors if we're not careful. Local exhaust from near sources that you can see up in the upper right in this image, portable air cleaners, mechanical systems with filters in them. And then the numbers that you see on this plot indicate that the concentrations or the levels of fine particulate matter can vary from outdoors to indoors, and even in the personal breathing zone of an occupant indoors who tends to put themselves close to sources. Superimposed on all of that is that all of these things happen dynamically. There are rapid changes that happen that change everything that's happening in this diagram on the order of minutes, sometimes even tens of seconds. And there's significant gradients from room to room in a building or classroom to classroom in a school. So it's a very complicated system we're dealing with. We're going to start with sources of indoor fine particulate matter. And I've circled here the topics that were covered in the workshop: outdoor sources, indoor sources, chemical reactions that lead to particle formation. And though while not a source, it's really a sink, there was some discussion as well about particle deposition onto surfaces. So for this workshop on April 14th, presentations addressed outdoor and indoor sources that I just said, transport mechanisms and how particles penetrate from outdoors to indoors, outdoor sources and chemical transformations that occur when outdoor fine particles come indoors. And that's a really important issue. Emissions from cooking, which we observe to be probably one of the major sources of indoor fine particulate matter. Secondary or aerosol formation, that's from chemistry that happens indoors. The effects of humidity on indoor fine particulate matter, and influence of various sources on characterization of exposure and health effects. So to kick off the first session, we had Kasenica Ivy, who at that time was at UC Riverside, is now at UC Berkeley, and she talked about indoor particulate matter of outdoor origin. Every one of our presentations was just so chock full of information. I can't tell you everything that every speaker said, so you'll have to read the report for the fine details. But I did write down just a few things that really struck me about each talk, and I'll mention those. Kasenica mentioned a wide range of outdoor sources, but one of the things she said that really struck me was the largest sources of outdoor fine particulate matter are not necessarily the most important. And she gave the example of diesel particles, which can be particularly toxic, but when you look at total source emissions, are relatively small compared to other sources of fine particles. She talked about proximity of sources to buildings and how much that matters, and significant inequities in land use patterns because certain groups in society, certain marginalized groups who live near freeways and industrial sources, can be exposed to a lot more of these outdoor particles inside of buildings. And she discussed a study she was involved with where areas of greater poverty had greater PM 2.5 exposures in the home. And that was due to activity patterns, the nature of the homes that people that are in marginalized communities live in, as well as the nature of sources in the homes. Brent Stevens followed up with a really nice presentation on the mechanisms by which outdoor particles come into buildings. He defined what's called an infiltration factor, and that is what the fine particulate matter concentration would be indoors relative to outdoors if there are no indoor sources. So another way of saying that is, what's the attenuation of outdoor particles as they come indoors? And he reported a median value from all studies of about 0.5, which means that, on average, the median is about half the concentration of particles of outdoor origin exist indoors. One thing that really struck me was his assessment of microenvironmental PM2.5 exposures. And he estimated that 71% of fine particle exposures occur in the home, 20% inside other buildings, and 9% outdoors. And if you look at the attribution of where those particles came from, almost 50% are particles of outdoor origin, and 50% are fine particles of indoor origin. Brent was followed by Delphine Farmer, who talked about chemical transformations that take place when particles move from outdoors to indoors. She said that the general trends for outdoor fine particulate matter in the United States is a decline in outdoor PM2.5, except for in Western states because of wildfires, where we're actually seeing increases. Outdoor particulate matter, when it comes indoors, is transformed. It's transformed because of temperature gradients. If it's cooler outside and particles from outside come inside and it's warmer inside, you're going to evaporate some of the volatile fraction of those outdoor particles. If it's colder inside than it is outside, you get condensation and grow those particles. There's thermal partitioning. There's uptake into the particles of all sorts of chemicals like plasticizers and flame retardants that we see higher levels of indoors and outdoors. And she also mentioned that oxidative potential of PM2.5 is important in terms of the effects on human cells and oxidative stress, and that oxidative potential can be significantly affected by these types of transformations. Again, a complex system, lots going on. The second session on April 14th dealt with indoor sources of fine particulate matter, and Nina Vance from CU Boulder kicked us off talking about cooking as a major source of indoor fine particulate matter, and particularly if people cook without an exhaust fan on, where you can get hundreds of micrograms per cubic meter of fine particulate matter building up inside of a home. She found that emissions are a function of heat source and food or cooking oils that are used. Particle numbers that are emitted are dominated by the fuel source, whether we're using natural gas, electric burners, or induction burners. And that emissions and the composition of the particles is highly variable, and it really depends on ingredients, oils, heat source, temperature. And she showed a lot of great data from a large study that happened about 3 years ago called the Home Chem study in a home with lots of monitoring and events over the course of a month. Nina was followed by Michael Waring, and Michael talked about indoor chemistry and the formation of particles, particularly from these nice smelling terpenes that are used in a lot of fragrance and cleaners, green cleaners, and that type of thing. And when you mix those with ozone, you get these bursts of oxidized products. Some have low vapor pressure, and you form organic aerosols from self-nucleation or condensation on existing particles. He did mention that as a source of indoor fine particulate matters, chemistry is generally a small contributor to the overall mass, unless the terpene levels and the ozone levels are very high and the air exchange rate is very low, so that chemistry has time to happen. He did express concern regarding some air purifiers that can emit large amounts of ozone and drive such chemistry. He was followed by Lindsay Marr, who spoke about the effects of humidity on the chemistry and biology of indoor air. Lindsay mentioned that humidifiers can emit fine particulate matter, particularly based on the amount of minerals in the water that is being used. She mentioned that relative humidity affects chemistry through evaporation and condensation processes. It can affect the size of particles, and as particles shrink because of, say, low relative humidity, then whatever's in those particles that's not volatile is concentrated to higher levels, essentially. Relative humidity affects microbiology. Mold thrives at high relative humidity. Bacteria survives worst at low relative humidity, and viruses survive worst at mid-relative humidity. So RH turns out to be a pretty important parameter for a lot of things going on in the indoor environment. Andrea Farrow ended the first workshop day and reminded us of, Andrea's from Clarkson University, and she reminded us of the personal cloud or pig pen effect, which basically means that if we measure fine particulate matter concentrations in room air, oftentimes in our breathing zone, they're actually much higher because we tend to place ourselves close to sources. For example, when we're cooking. She really stressed that indoor sources of fine particulate matter are dynamic and often occupant driven. You know, somebody turns on the stove to cook, doesn't turn on the stove hood to vent, decides to burn candles. Those are occupant decisions that lead to particulate matter indoors. She really stressed that we don't know really anything about the effects of peak exposures on human health. And she also stressed disparities in sources, built environment, the amount of people in a home, HVAC systems or not, the amount of infiltration and big gaps in the building envelope, activity patterns related to marginalized communities that can lead to much higher fine particulate matter exposures. So kind of a summary of the workshop discussions were, I've already addressed some of these, so I'll go through these quickly, but situational factors are important. Where a building is located, the time of year can have an impact. If you're in a place that has significant photochemical smog and particle formation in the summertime, that's important. If it's western wildfires in the late summer and early fall, that's important. Humidity levels are important, as we just discussed. Building and HVAC system characteristics are important. Occupant activity and mobility patterns. Do we have people in homes that are staying home all day long, 7 days a week? Occupant perceptions of indoor fine particulate matter are important. We'll get to that a little bit later as well. And I think all of the participants expressed a strong sentiment for addressing the underlying causes of exposure disparities in our society, that some members of our society are exposed to a lot more fine particulate matter than others. The research needs are to better understand how particles move from outdoors to indoors, to develop health relevant source metrics. There was a strong sense that there's so many sources. How do we know which ones are the most important in terms of the fine particles that are emitted? To explore chemical deposition and sink processes that affect indoor fine particles, better characterize input parameters so that we can develop better models to predict what's happening indoors, enhance knowledge of the composition of indoor fine particulate matter. You'll hear this again. We just don't know that much about the chemical composition of particles, and it's really hard to actually characterize that in a routine way. And examine the interactions between indoor fine particulate matter and indoor microbiomes. Overall, there's a need for systemic solutions to systemic problems that affect marginalized communities in our nation. So the second set of workshops was on April 21st, and now we move from sources into really health effects and exposure and health effects, and then how we assess those things. So we're focusing now on the complex part of the system that is the actual occupant themselves and the health effects on the occupant. Presentations address the health effects of exposure to indoor fine particulate matter, the overall health burden of indoor particulate matter exposure, pulmonary disease associated with indoor fine particulate matter exposure, and again, disparities in economically challenged communities, the health effects of indoor exposure to wildfire smoke and other outdoor events, technical complexities of how to measure PM 2.5 and how that fits into estimating exposure, and the challenge of moving from just measurements to actually determining exposures. And what are the utility, use, and misuse of low-cost consumer indoor PM sensors that are really proliferating these days? So the first speaker in this session was Howard Kippen from Rutgers University of Public Health, Rutgers School of Public Health. And he talked about the overall and mostly cardiovascular health burden of indoor fine particulate matter. Howard mentioned that a lot of epidemiological studies have been conducted on outdoor PM 2.5, and they're associated with mortality on the order of 230,000 to 300,000 deaths per year in the United States. He did say that cardiovascular effects dominate, but chronic and acute respiratory disease is also important. We often study the impacts in terms of biomarkers, and there's still a lot of research that's needed to find the best biomarkers for exposure. One thing that struck me from Howard's presentation was his statement that 40 to 60% of total mortality attributed to PM 2.5 is associated with indoor particulate matter, all right? So a lot of the health burden of fine particulate matter that we see in epidemiological studies that rely on outdoor monitoring, at least on the order of half of the mortalities are due to exposure indoors. And he made a statement that stuck with me, which is outdoor epidemiology is indoor epidemiology when we're talking about fine particulate matter. Howard was followed by Meredith McCormick from Johns Hopkins University School of Medicine, and she focused on pulmonary disease associated with fine particulate matter, again, with a focus on disparities in economically challenged communities. Meredith indicated that increases in fine particulate matter are associated with increases in asthma and COPD morbidity, and there's plenty of literature to show that portable HEPA air cleaners can reduce these symptoms of asthma and COPD. Exposure to PM 2.5 affects the trajectory of lung development in children as our lungs continue to develop until our early 20s, and that PM 2.5 has synergistic effects on asthma systems for overweight and obese children. Meredith was followed by Stephanie Holm from the University of California, San Francisco, who really focused on wildfire smoke. And Stephanie mentioned that for wildfires, the way we protect ourselves from particles, PM 2.5 associated with that smoke, is to tighten our building envelopes, control ventilation, and use really good filtration during wildfire events. And that combined, this has been shown to substantially reduce fine particulate matter indoors. She indicated that proper filtration can reduce hospital admissions by greater than 50% during wildfires, and that, like many of the other speakers talking about environmental justice issues, wildfires pose significant environmental justice issues because the things that we have to do to protect ourselves during wildfire events are often not able to be attained by those in underserved communities who don't have the resources to pay for things like portable HEPA air cleaners and tightening of the building envelope if they even own the building that they're in, the home that they're in. So we went from health effects then to sort of exposure and assessment, and Bill Nazaroff kicked off the second session of the second day and talked about 4 dimensions of complexity associated with indoor fine particulate matter. He talked about the wide range and sizes of particles within the PM 2.5 designation. And I already told you about the Etruscan shrew or the gray whale analogy in terms of volume of particles. Talked about temporal complexity, that things change on the order of 100. You can have 100 times difference in fine particulate matter if there's a new source that's emitting literally within minutes in an indoor environment. There's chemical complexity. There are huge differences depending upon the origin of the particles in terms of what they're made up of, and spatial complexities in terms of sort of the heterogeneity across buildings, even across rooms in the same building, even within the same room in a building. And he said that no instrument can do it all, and that we need to find ways of simplifying the complexity to the extent that we can without losing the objective analysis of how we reduce exposure. He was followed by Kirsten Kaler from Johns Hopkins School of Public Health, and Kirsten focused on what we know about exposure. One thing that struck me in her presentation was that unlike many pollutants, say pesticides, for example, there's no magic biomarker for PM 2.5, and that makes doing exposure studies very difficult. That measurement is not equal to exposure. That large, low-cost sensor arrays can be used in cities to look at population, to roughly estimate population exposure, but they don't capture what's happening at the individual level. And that really the creme de la creme is personal monitors tied to GPS systems. And even when we do that, if we take a cohort of people all starting at the same location and we measure their personal exposure with monitors that are on their bodies, right? And we track where they go, we get wide differences between individuals, wide differences by day of week between individuals. She did indicate that there was a study where GPS systems were used for children with asthma in Baltimore. And what was found was the single most important environment for their exposure to fine particulate matter was their homes, dominating all other environments. Following Kirsten was Dusan Lacina of the Swiss Federal Institute of Technology. He spoke about these low-cost consumer indoor particulate matter sensors that many people are using now, rapid growth in these things. He said that these $200 or less systems can give you actually really good results when you compare them against a very expensive reference instrument in a laboratory but as soon as they go out to the field, they don't give as good of a result relative to good reference instruments. And they're influenced by the nature of the particle composition, by the size of the particles, a lot by the relative humidity, bringing back relative humidity again. They can be very limited at fine particle concentrations, less than 20 micrograms per cubic meter. So they're best if you have, like cooking events that are unvented and you have very high particle concentrations indoors. A lot of potential with these instruments, but there's still a lot of work to be done. So I've covered a lot of the summary of the workshop discussions for this so far, but I think the main points are indoor fine particle health burden is a significant problem worth caring about, and the committee felt that was a strong statement that we needed to make. Measurement is important because it influences how we understand, attribute, and quantify health burden. It informs and validates control efforts. So if we turn on a portable HEPA air cleaner and we see a quick 90% drop in particles, then measurement tells us that it's working, for example. And then measurement of PM and health burdens is actually really complex. And again, I'm not going to go through all the points on this slide, but I do think it's important that complexity is woven into this. Are we talking about acute versus chronic? Are there interactive effects where we're talking about an obese population or a population that has other diseases that are impacted by PM 2.5 more than the average population? And study methods may determine what is measured or determined, and we need more focus there. The challenges with exposure and health effects are that it's easy to mischaracterize exposure if we don't take great pains to try to do it right. For example, personal monitors with GPS systems included. It's sometimes challenging to understand what metrics should be used. There are opportunities for the development of new measurement tools and methods, but there's still a lot of research that's needed in that area. So that finished the second day, and the third day was on mitigation of indoor exposure to fine particulate matter. So here we're talking about using ventilation to our advantage, portable air cleaners, local exhausts, say when cooking, good filters and mechanical systems. And even here, and I've circled the occupant because human behavior is important for mitigation of indoor exposure to fine particulate matter. And that comes into play in terms of education and also giving a sense to occupants of buildings whether they need to do something to change the air quality in the building. So for mitigation of indoor exposure to fine particulate matter, remember we're focused on practical mitigation. The presentations address means of limiting exposure by filtration of PM 2.5, PM 2.5 exposure control in schools, mitigation of PM 2.5 exposures associated with cooking, portable indoor air cleaners, and human behavior in terms of their use, how building occupants interpret and respond to indoor air quality sensor data, and then public health responses to reduce community exposure to PM 2.5. This session was led off by Jeff Siegel. He talked about filtration primarily in mechanical systems and HVAC systems. And Jeff said that most residential HVAC systems only recirculate air. They don't bring in outdoor air. Only a very, very small fraction of residential HVAC systems are actually designed to bring in outdoor air. They only recirculate a small percentage of air inside of a building. The median time that a mechanical system is on in North America, it's about 18% of the time. So even if you have the world's greatest filter in your mechanical system, 82% of the time it's not doing anything. The effectiveness of filtration depends on a number of factors: the volumetric flow through the system, filter efficiency, fraction of time that it's on, whether there's bypass around the filter, and so on and so forth. Filters can work well with enough flow if it's a good filter, if it's properly installed, if it has a high runtime. Jeff mentioned that in the future we should probably think about how to link particle measurements indoor with activation of the mechanical system so that it turns on whenever particle levels are above a certain threshold. And he also cautioned us that there are other particle control technologies on the market besides filtration that are lacking independent evaluation and that he feels can cause potential harm. So Jeff's focused on residential filtration in mechanical systems. He was followed by Elliot Gall from Portland State University, who talked about fine particulate matter exposure control in schools. Struck me, Elliot's presentation, 15% of schools are within 250 meters of major roadways, and a high percentage of those schools that are close to major roadways are schools that are primarily Hispanic, Black, and Asian serving. Exposures to transportation-related pollution is associated with asthma exacerbation and cognitive decline. There are studies in the literature that suggest this. So schools located near busy freeways and highways are a concern. He talked about a study in a middle school in Portland, Oregon that he was involved with, attempting to reduce children's exposure. This was a middle school right next to Interstate 5 running through Portland. And he found that the position of the air intake with respect to the freeway has a huge impact on potential exposure of the children in the school. If the air intake is as far away from the highway as possible or freeway, you can get upwards of 60, 70% reduction in exposure just from the placement of where the air intake is. He also suggested that you can reduce exposures by having outdoor time in the school when the children are on the playground linked to traffic patterns. And then improved filtration in the HVAC system in the school that he studied led to an 85% reduction in black carbon associated with vehicular traffic emissions. So pretty striking results to reduce children's exposure to fine particles in a school. Elliot was followed by Brett Singer, who talked about particulate matter exposure associated with cooking, that cooking emissions are extremely important, a major source of indoor fine particulate matter, that local exhaust is important. The best mitigation is with a range hood with a vent that works. It's also possible to have downdraft exhaust on some stoves, wall exhaust if it's not tied directly to the range or stove, or open windows. The best case scenario for controlling emissions is to cook on back burners. Cooking on the front burners gives a dramatic decline in the capture of particles by the vent hood. It's important that the vent hood be on its highest flow setting, and hoods that are extended to come out further towards somebody who's cooking also give a lot of benefit in terms of capture of particles. What was shocking was the number of people in a study by Lawrence Berkeley National Lab who have the ability to use a range hood and to ventilate particles, but that do not. And that goes back to occupant effects. A lot of people have the ability to control, but don't. In the second session of the last day, we talked about occupant responses to indoor fine particulate matter. And this was led by Stuart Batterman of the University of Michigan School of Public Health. And Stuart talked about the fact that portable HEPA air cleaners can significantly reduce indoor fine particulate matter under the right conditions, but only if used, again, just like using that range hood vent. There was a study of 89 families in Detroit that he was involved with, where a significant reduction in PM 2.5 was found when HEPA air cleaners were used in children's bedrooms. They had 97% of participants using the HEPA air cleaners on a regular basis at the start of the study, but that dropped over the course of the study all the way down to 28% of the time after a few months. And some were only using it 5 to 10% of the time. So the issues that came up with individuals in this study were that the portable air cleaners were noisy, and so they turned them off. They didn't like the draft, the airflow that was caused by them, and they were concerned about their electricity bills. It's roughly about $200 annually to run a HEPA air cleaner continuously. I believe in this study, the individuals were actually paid for their electricity costs, but they were still concerned about that and mentioned that as a reason for not wanting to use it. Stuart advises parents to put HEPA air cleaners in their children's bedroom, especially if the child has asthma, and leave it on always. Never turn it off. Otherwise, if somebody turns it off too often, it never gets turned back on. Stuart was followed by Lindsay Graham from the University of California, Berkeley, and she talked about building occupants and how they interpret indoor air quality data and what they do with it. She indicated that people's perception of indoor air quality is impacted by odors in a big way, including cooking, temperature, relative humidity, and airspeed, none of which might actually be related to indoor air quality issues, but at least they really drive the perceptions of occupants. She said that we need to somehow find ways of getting occupants tuned in to actual pollutants and measurements. And that in her studies and other studies, people do not like complexity and information. They want the simplest possible information that allows them to take action. In one study, occupant responses to sensor outputs were determined based on numeric output, scale, so think about like a bar going up and down as particle levels change, or some kind of health indicator that indicates things are unhealthy right now. And what was found in that study was by far what people responded the most to was the statement that things are unhealthy right now. So health and an indication of health or unhealthy conditions is really what drives people to take action and do something. And if told that the environment they're in is unhealthy in the moment, they tend to be more active with respect to doing something about it, like turning on the stove range hood, or turning on a portable air cleaner, or opening a window. And then Lindsay was followed by Sarah Cofield from the Missoula City County Health Department in Montana. And Sarah gave a really nice presentation on sort of public health workers and public health responses to reduce community exposure to indoor fine particulate matter. Sarah's in a part of the world that has a lot of wood burning stoves that lead to high fine particle levels, both outdoors and indoors during the wintertime, but also in an area that's really prone to impact by wildfires. So she gave very practical advice, and she talked about important factors that happen, say, during wildfires, is foot traffic for businesses or schools. How often is the door opened? And that can lead to sort of gushes of fine particulate matter coming indoors. Ventilation, are people keeping their doors and windows open or closed? Sometimes it's hard to change human nature, especially in the summertime during wildfire season where people don't have air conditioning and so they leave their windows and doors open. Sensor positions, they distribute low-cost sensors and try to show how the use of HEPA air cleaners or shutting a window can actually change the indoor air quality. And then air handling unit settings and maintenance. So she said that the population doesn't have a lot of patience. If during a wildfire event, they have to shelter in place, there tends to be wildfire fatigue for shelter in place after a few days. And it strikes me when she said that we can sort of relate that to the pandemic that we're dealing with right now, is that people just want to kind of get on with life. And after a few days, they start opening their windows, going outside, they have wildfire fatigue. So messaging and communication is really, really important. Interventions are important. Handing out HEPA air cleaners to vulnerable populations, providing clean air shelters in libraries and cities, and then all of the policy work that's needed to make decisions such as should we close down schools or not during wildfire events. So, in summary, for mitigation, improved filtration of indoor PM 2.5 we know is associated with subclinical cardiovascular benefits, increased birth weight, reduced asthma morbidity, higher test scores. There are a lot of benefits when we filter and reduce indoor PM 2.5. Cooking is a major source of indoor PM 2.5 and can be mitigated with a range hood and other ventilation sources, downdraft exhaust, etc. Occupant behavior is key to mitigation. This is something that was really stressed by the workshop speakers. Filtration only works with a good filter properly installed and operated. You can have the best filter in the world, but if you don't install it well and it's not operating, you're not going to get much bang for your buck. It's important to mitigate indoor fine particulate matter levels in schools, and significant reductions in traffic-related air pollution can be achieved with proper filtration and efficiently operating HVAC systems in schools. Presentations highlighted indoor mitigation issues and opportunities associated with portable HEPA air cleaners, high-efficiency particulate air cleaners, and they can significantly reduce indoor PM 2.5 and based on previous studies, yield health benefits if they're used. They can be valuable mitigation tools during wildfires, and messaging is critical for reducing exposures to PM 2.5 during wildfire events and other significant outdoor events. And really preparing for those events is very critical in areas that are prone to wildfires. So I'll end the sort of summary of the workshop discussions by saying that substantial exposure and health disparities are related to socioeconomic status. Underserved communities carrying a very high burden with smaller homes, older ventilation and exhaust systems, if they even have them, and economic challenges that affect their ability to implement practical mitigation approaches. This was a very strong thread throughout every day and every session every day of this workshop. Again, we're dealing with a complex system. I hope that after hearing what I just said, you'll realize that it's a complex system. There's still a lot of research that's needed to better understand the system and to optimize, if you will, strategies to protect everybody in our population from exposure to fine particulate matter. There's a long history of the National Academies indoor environment reports. You can see some of them here dating back to all the way to 1987, dealing with indoor allergens and asthma and damp indoor spaces. I've actually read several of these myself, and they're really chock full of great information. Indoor air quality and the health of green schools, climate change in the indoor environment, health risks of indoor exposure to particulate matter, another workshop that I was involved with in 2016 that had just tremendous amount of information, a great benchmark for what we knew at that time, and then microbiomes of the built environment. Current related National Academy studies include the Committee on Emerging Science on Indoor Chemistry, which is examining the state of the science regarding chemicals in indoor air. I'm not going to read through all of this, but I will say that one of the things they are looking at in that committee is chemistry that leads to particle formation. So we were fortunate to have one of the committee members from that committee on our committee, Kim Prather, and she helped us to make sure that we didn't kind of overlap too much with what that committee's doing, and we didn't. So it was a very nice compliment. Their report is expected to be released in the spring of 2022, and you can find information on this study at the link that's shown on this slide. The Committee on Health Risks of Indoor Exposures to Fine Particulate Matter and Practical Mitigation Solutions, which should sound familiar because that was the title of our workshop, is now an official committee conducting a companion study to the workshop that is reviewing the recent scientific literature on the health risks of exposure to fine particulate matter, and will offer recommendations for engineering solutions and interventions to reduce risks of exposure to it, including practical mitigation. So we're just basically going to do a deeper dive into all of the things that were considered in the workshop. That study will be completed in early 2023, and information on it may be found at the link that you can see at the bottom of this slide. And for more information on our workshop, there is a workshop report and online information related to the workshop, including links to all of the presenter slides, and you can find those at the link in the middle of the slide. The proceedings may be read online and downloaded in digital form at no cost, and you can see the link for doing that. And the study's email address is indoor-pm@nas.edu. And that pretty much concludes the presentation, and I guess we're ready for questions and answers.
Great, Rich. Thank you so much. You covered a wealth of information there, and a lot of folks asked during the presentation about where to find the recordings of the presentations from the workshop. And so if folks are interested, the link for that is in the chat box for you. We do have a lot of questions, so I will jump into some of those. One of them was kind of overall about the workshop, the scope of the workshop. You talked a lot about residential exposures, a little bit about school exposures. Could you say a little bit about kind of why you chose to focus on those, and if there's other building types that we might want to be concerned about particulate matter in?
Yeah, sure. So again, I think you can see from the presentation that just focusing on residences and schools was a large task, right? There's a lot of information, a lot of nuances about both of those environments. So we decided to reduce the scope to residences and schools. I think focusing on residences makes a lot of sense for the reasons that I mentioned at the beginning of the presentation. We spend 54 of our 79 years of life on average inside of residences. So if we're going to focus on a specific environment, that is the most probably important environment to spend our time on. It's also an environment where those in underserved communities, marginalized communities, spend an even greater amount of their time. And the residential buildings that they spend time in tend to have all sorts of issues that many don't have to deal with in the residences. We chose schools mainly because we wanted to have an environment where we could focus on children. I think that's a key reason to focus on schools. And certainly there are a lot of concerns about schools during the pandemic, and this workshop did happen during the pandemic, and the exposure of children in schools to bioaerosols that contain viruses. But when we talk about practical mitigation of fine particulate matter, if we can do that in schools, independent of what the source of the fine particulate matter is, it will benefit all aspects of children's exposure to respiratory aerosols that contain SARS-CoV-2, so virus. So it had that kind of extra value added in studying schools. So those were the two main reasons we chose those environments over any others.
Great, thank you. We have a few questions here about the sources of indoor particulate matter that you talked about a bit at the beginning of the presentation. One of the questions was, did the committee consider the impact of radon decay products, including translocation, that are likely attached to a substantial portion of PM? And if not, is there any interest in pursuing this topic in the future?
So the committee did not consider that, and none of the speakers that we selected considered radon decay products and attachment to fine particulate matter. There has been a lot of work on that topic in the past, and again, just trying to narrow the scope. We couldn't cover everything, so we did not cover that. And that might be something that comes up in our deeper study, which is going on right now, a deeper assessment.
Okay. Excellent. Another question about sort of how how outdoor particles affect indoor air. What particle sizes are best able to cross the building envelope? And does the size distribution of indoor particles of outdoor origin differ from those that are outside?
Yeah, that's a great question. So the size distribution, I'll answer the second part first. It really depends on the source. So, the particle size distribution from cooking is a lot different than the particle size distribution from resuspending stuff off the floor when you walk into a room, or other sources of indoor particulate matter. And the same is true for outdoors. If we took like a collective particle size distribution outdoors, and we collect, it may be a lot of times very similar to what we find indoors. It depends on what the indoor sources are in comparison. So I'd say the indoor sources vary. The particle size distribution varies a lot more indoors, just because of the nature of the different sources that are turned on and turned off at any given time. The first part was about particle sizes that penetrate through the building envelope. Turns out that very large particles don't penetrate as well as PM 2.5. So if we're talking about wind-blown dust outdoors, it has they're not as they're essentially, if you can think of it, sort of filtered out by the building envelope much easier than the building envelope removes PM 2.5 moving through. And if you get to extremely small particles, which are impacted by what's known as Brownian motion, a lot of variation off of their what's called streamlines as they're moving around the cracks and windowsills and that kind of thing. The really small particles are also reduced in their penetration into the indoor environment. So the kind of happy medium is the sort of PM 0.5 to 2.5 micron range has a very high degree of penetration through most building envelopes.
Excellent. Let's see. We have another question here, kind of generally. What are some of the best ways to avoid exposure to particulate matter when you're cooking?
So the best way and the easiest way is ventilation. So if you have an exhaust fan on your range hood, use it, and use it on the highest flow setting. All of the data in the literature indicates that that will give you your maximum reduction in exposure while cooking. If you do not have a range hood that ventilates, that I've bought homes in the past that have a hood with a fan in it that just recirculates the air back into my face, and I've had to retrofit to put an exhaust duct up to my roof. If you have that kind of thing, it's not going to be helpful to turn on your exhaust hood, and so then you'll have to deal with opening windows in the kitchen if you can, get some cross flow of air to reduce the levels of particles in the kitchen. Oh, and I should have mentioned, as I did previously, one of the things that's most striking about cooking is if you have an exhaust fan, cook on the back burners to the extent that you can, especially if you're really heating up and frying and that type of thing, or if you're using gas burners. Back burner cooking dramatically reduces your exposure to fine particulate matter relative to cooking on the front burners.
Great. Another related question about cooking is, sometimes people might choose to not put the hood on because they don't think they need it, or maybe they like the smell of the food or something like that. Is there a good indicator of kind of when you need to turn the range hood on, or, kind of what the level might be in your home while you're cooking?
Yeah, so, I mean, the recommendation should be to always put your turn on ventilation of your hood when you're cooking, right? Yeah, I would say always. And I'm not quite sure how to answer that question otherwise. I think the safest thing to tell people is to ventilate while you're cooking.
Yep, that makes a lot of sense. Another question kind of related to some of the topics in the sources, the data that's focused on sources, was you discussed how relative humidity is important to PM levels. Are humidifiers that use tap water considered to be an important source of PM 2.5 indoors?
Yeah, it depends on the mineral content of the tap water. So if you have high mineral content, then when you humidify, you can emit a fair amount of fine particulate matter, which is going to become essentially airborne minerals from the water. So it's going to depend on where you are and what the mineral content of the water is.
Okay. One kind of last question, I think, on sources. This question is about fibers from things like indoor carpeting and clothing, and how, are those a source of particles? How might those impact the levels of particles indoors?
Yeah, certainly they're a source of particles. We didn't really deal with those types of particles because they tend to be outside the PM 2.5 range, so they tend to be larger particles. And we were really focused on fine particulate matter. But anytime you have a group of individuals, say, walking into a classroom or any kind of indoor environment, you can, if you're measuring for it, detect particles that are coming off their clothing, whether it's the clothing itself and clothing fibers, whether it's dust that's on their clothing that gets resuspended back into the air. And certainly when people walk, the forces of their feet on the floor tend to resuspend particles around the floor. That tends to be larger particles, dust-like particles that generally are larger than PM 2.5. And so in our workshop, there was some discussion of them, but largely we focused on the smaller particles, PM 2.5.
Great. I see another related question here about sizes. Did you look at all at particles kind of in the ultrafine or nano range?
Yeah, there was discussion of ultrafine particles, and that came up especially in the session on health effects. Certainly, cooking also generates, especially if you're cooking with gas stoves, you can generate a lot of ultrafine particles. And those things were noted in the workshop, and they are discussed in the workshop report. And I think we kind of came into this with the there's a debate kind of in the community: is are ultrafine particles considered part of PM 2.5? And in my mind, they are, because PM 2.5 should be everything less than 2.5 microns, and ultrafine particles are particles less than 0.1 microns. So they were considered by a number of speakers, especially as related to cooking and especially as related to health impacts. And all that information is included in our workshop report.
Excellent, thank you.
I think there was a general sense that ultrafine particles are a concern with respect to health impacts, especially ultrafine particles associated with certain sources, transportation-related sources, for example, and that more research is needed in that area related to health impacts.
Excellent, thank you. I think our next question is moving into the kind of metrics and assessment area. What would be the significance of setting a threshold for PM 2.5 exposure? And kind of how would that be, how could that be used if we could do that?
For indoor environments? Or
for indoor environments, yep.
Yeah. So that's a really complicated question. You could get together, 25 world experts on PM 2.5 and health, and probably it would take a long time to come to a consensus as to what that threshold would be. That there's still work to be had in trying to determine, at what point are there minimal health effects, right? So the other problem with that is measuring PM 2.5 in residential buildings or school buildings. To do it right, to do it accurately, requires instrumentation that can cost in the tens of thousands of dollars for each indoor environment that you're studying, right? So this goes back to the presentation on low-cost air sensors, these $100, $200 devices, which have a lot of promise, but they're not quite there yet in being accurate enough for us to take the numbers from them and compare them with a threshold. In indoor environments, the same, a system might be accurate to a factor of 2 or 3. And so if you set a threshold of 10 micrograms per cubic meter and you're reading 30 micrograms per cubic meter, that might actually be below the threshold, but the instrument isn't accurate enough to tell you that, if that makes sense. So I think the hope is that as we continue to advance these low-cost sensors, we can get to a point where they could be used in mass in indoor environments, and that we could link them to a threshold that would tell us, you're now above this, so your mechanical system should turn on, and actually have the reading linked to a mechanical system, for example. Or to tell the occupants of the building, you now have unhealthy conditions, you should open a window or turn on your HEPA air cleaner or that type of thing. So there's, I apologize for not giving a firm answer, but I think everybody would like to get to that point. It's just that we're still not quite there.
Definitely, that's very understandable. Thank you for giving that one a shot. I have another question that's related to the low-cost sensors that you were talking about. Based on what you learned during the workshop presentations, is there anything that you would recommend that folks consider if they're thinking about getting an indoor air quality sensor?
So I don't like to recommend specific brands of anything. I've always tried to avoid doing that. There have been some studies recently that have very good comparisons of side-by-side analysis of low-cost particle sensors, and at the same time compared with very expensive particle analyzers. So one of those studies was published about a year ago. The researchers were at Lawrence Berkeley National Lab. I think if you go to the Lawrence Berkeley National Lab Indoor Environment Department website, that you might be able to get information on their findings. I believe Brett Singer, S-I-N-G-E-R, was one of the authors of that study. And I know that there's another group right now, because I'm involved with it, who's doing a similar comparison of low-cost sensors that were used during the home chem study that I alluded to previously. But we're still analyzing all of the data, and it hasn't been submitted for publication yet. But I will say that there are certainly differences in the performance of different low-cost air cleaners in the field. But even the best, we cannot consider to be accurate enough to develop things like, to help us to see whether we're meeting thresholds or not. So the best thing I can do is give advice to check out a recent publication, I think it was about a year ago, by Lawrence Berkeley National Laboratory, and they call out specific low-cost sensors and how they performed.
Great. Another question on measurement. What is the difference between measuring the mass of particles versus the numbers of particles, and what information can you get from those two pieces of information? Yeah,
so great question, and we had some discussion about this, and there is debate, particularly from the health effect standpoint, as to which one's better to use. I think the kind of emerging consensus is that certainly for ultrafine particles, number concentrations, the number of particles per cubic centimeter of air, or the number of particles per cubic meter per air is the important metric for ultrafine particles. When we get into fine particulate matter, then I think we start moving more towards mass. I will say that even for ultrafine particles, which you have to have a lot of to actually measure reasonably high mass concentrations, that can happen with cooking events, particularly if you're cooking with natural gas. So if you're cooking for a prolonged period, say an hour with natural gas, you can not only get extremely high number concentrations of ultrafine particles in an indoor environment, you can also measure pretty high mass concentrations of ultrafine particles in an indoor environment. So there's certain sources where the number of ultrafine particles emitted are so significant that mass concentrations are actually relevant. But otherwise, I think the tendency is for ultrafine particles to focus on number concentrations. And then there's debate when you get above ultrafine particles as to whether we should be using solely mass concentration, particle number concentration, or both in terms of reporting.
Excellent. Another question about kind of the metrics area of things. Are resources like airnow.gov a good reference for kind of making decisions about how to control building HVAC systems, for example? How could kind of the outdoor data be used to help us make decisions about things like that to control our exposure to PM?
Yeah, so that's a great question. And I think that we can use outdoor fine particulate matter measurements to know, how much fine particulate matter is outdoors, especially during wildfire events, or if we're close to certain industries, say they're flaring at an oil refinery or something like that, and we live downwind of that. Those measurements can be really, really valuable and suggest to us when we really need to close windows, close doors, turn on our portable air cleaners, or activate our thermostat on continuous fan mode to run air through a good filter and a mechanical system. So I think they can advise individuals on actions that they should take inside their homes to reduce the amount of penetration of those outdoor fine particles into their homes. And schools could do the same.
Great, thank you.
And let me add that in terms of controls, I think that I'll give a pitch here to the US EPA, but the US EPA has a really good website. And I don't remember the exact link at the moment, but that does give a nice summary of control devices that can be used indoors to reduce fine particulate matter. So if you go to EPA.gov and the indoor air quality page on EPA.gov, there's some really good information that can be downloaded on portable HEPA air cleaners and other devices. Filtration. Yeah.
Thank you so much for that. Excellent plug for our website. And I see that we've just drop that in the chat box for folks who are interested in visiting. EPA.gov/IAQ. So I think we'll move on to some questions about mitigation. One of the questions was about air exchange rate. How does mechanical air exchange affect the concentrations of fine particles indoors?
So a great question, and ventilation can be tricky for indoor fine particulate matter, because remember that much of the particulate matter that we see indoors comes from outdoors, right? So that 50-50 rule in terms of where the particulate matter comes from indoors that we inhale. So if the source of the particulate matter is indoors, cooking, or some other source, some hobby that somebody does, somebody likes burning candles, those types of things, then ventilating, increasing ventilation can be very valuable for reducing fine particulate matter levels. That's if the primary source of the particles is indoors. If it's a wildfire event, or you have very high outdoor particle levels and you don't have significant indoor sources of particulate matter, then you want to reduce ventilation to reduce the amount of outdoor fine particulate matter that comes indoors. So it really matters as to where the main source of the fine particulate matter is. If it's an indoor source is dominating, then ventilation is important. For example, you're cooking. If it's the outdoor environment that's dominating, it's very bad outdoor conditions, high particle levels, then you want to reduce ventilation. During COVID, that can be problematic, especially for families that have a lot of people at home. If somebody's sick and you're telling them now to reduce ventilation, and that's where things like portable air cleaners can really come in handy, because they can give you the kind of equivalent effect of increasing ventilation in terms of reducing aerosol particle levels or fine particulate matter levels inside the home.
Great. Let's see. There was another question about filtration. There's a lot of options for home air filtration out there. What advice would you give to homeowners that are trying to choose the right kind of filtration technology for particulate matter, like a portable air cleaner versus a furnace filter or something else?
So my philosophy is always to do both well. And so improving the filter rating that you use in your HVAC system, if you have a mechanical system, many people don't. Improving that from whatever your minimum efficiency reporting value is, MERV. Oftentimes homeowners have things like MERV 4, which captures, cat hair and that kind of thing, but doesn't capture fine particulate matter, or MERV 6 or MERV 8. If you can, if your mechanical system can handle it, and some older mechanical systems have problems with this, is increased to the highest MERV rating that's possible, MERV 12, MERV 13 in your mechanical system. The other question was about portable air cleaners. The proven portable air cleaner that we know works, and for which there are decades of great studies by highly qualified researchers in the published literature, are HEPA-based air cleaners, high efficiency particulate air cleaners. And you want to choose one that's right-sized for the indoor environment you're in. So for a large bedroom, a school classroom, a small apartment, a portable HEPA air cleaner with what's called a clean air delivery rate, or a CADR, on the order of about 300, which is 300 cubic feet per minute, can actually be quite effective at reducing the levels of fine particulate matter in that environment. There's a kind of a firestorm right now, if you will, of people building do-it-yourself air cleaners, and you can go online and probably find those, which are basically box fans connected to a box that's made out of MERV 13 filters. A lot of universities are doing studies on those and finding that they're, in many cases, as effective or more effective than HEPA air cleaners if they're constructed properly, and that's a big caveat, and can also dramatically reduce fine particulate matter levels in school classrooms or residences.
Thank you. You actually anticipated my next question about DIY air filters, so thank you for that. And let's see, there was another question related to portable air cleaners that, sometimes there's a reported kind of fatigue of using the portable air cleaner from the noise or from having to turn it off and on as you leave the house or something like that. Did the speakers at the workshop talk at all about, kind of how we could make that easier for people to maintain that behavior of using the portable air cleaner?
I think that comes down to education, right? And explaining to people why it's important to keep it on and how, going from a high setting, which can be very effective at reducing particle levels, to a low setting will still reduce fine particulate matter levels, but not as much, right? So even simple discussions like that sometimes are needed to get occupants of buildings to effectively use devices. There was some discussion about the proximity of the air cleaner to the source being very important. Jeff Siegel mentioned that in his presentation. He diverged a little bit from filters and mechanical systems to portable air cleaners and said the proximity to source was important, to having it closer to the source as opposed to far away from the source. Not wanting to have it, for example, near an open window where you're essentially treating outdoor air if it's coming in and the air might be clean, or you're treating the air as it's leaving out towards the window, right? So we don't want to have portable air cleaners near big openings to the outdoor environment. And there was, I believe, some discussion about the use of multiple air cleaners, or maybe that was another discussion I was recently involved with, that you can use more than one portable air cleaner. And that's where the do-it-yourself systems come into play, especially for people that can't afford portable HEPA air cleaners, because the do-it-yourself systems are about a quarter of the cost of a good HEPA air cleaner for the materials. But you could use two at lower settings to reduce the amount of noise. And those two at lower settings reduce the amount of noise, but still give you the same impact as using one in a high flow setting. In that particular case, you want to make sure that the devices, you never want to have two portable air cleaners right next to each other. Otherwise, one might just be taking in the exhaust of the other and cleaning what has already been cleaned air. So you want to make sure that they're separated in a room or an indoor environment, so that you don't get short circuiting between the two, if you will.
Great, thank you. We did have another question about portable air cleaners and kind of, what information was provided at the workshop about technologies that aren't necessarily HEPA filtration, but UV lights, ionizing equipment, that sort of thing, to control airborne particulates and also bacteria, viruses, and odor.
So great question. There was very little in the workshop about those technologies. The feeling of all of the speakers in the workshop who discussed portable air cleaners was that there's one proven technology, and that's HEPA air filtration. It's filtration. There was some concern expressed about some other technologies that are relatively popular, and the fact that the published literature suggests that they can be relatively ineffective, especially compared to portable air cleaners, and may also lead to chemistry from ozone and other oxidants that are emitted from them that can lead to new pollutants in the indoor environment. And I think for those reasons, there was just a general tendency to not address those technologies. So really, if you read the workshop report, you'll find almost nothing about technologies other than filtration.
Excellent. Let's see, we had quite a few questions about wildfire smoke, and kind of, I guess there's two parts here. What would you say are the most important steps for homeowners, for example, to take, or fewer people to take in their homes to reduce exposure to wildfire smoke. And the second part of that is for people who are setting up cleaner air shelters, maybe in a different type of building. Is there any other considerations that they might want to think about?
Yeah, that's a great question, and it affects so many people nowadays. We have a wildfire in California right now, and it's not wildfire season, and so wildfires have become just so much more predominant in the Western United States. And one of the speakers did mention that when we have big wildfires in the Western United States, it affects all of North America. Everybody sees elevated PM 2.5 levels to a certain extent. But the question is, what can homeowners do? And I think Stephanie Holm from UC San Francisco, UC San Francisco, did a really nice presentation on the best techniques for homeowners, which is, to the extent that you can, seal up your house. If you're really being impacted by wildfire smoke during that time, seal up your home the best you can. Close all of your windows. If it's really bad, I know personally from being in an area with bad wildfires, I was actually trying to reduce the gap underneath my door with wet towels in Portland a year or two ago. So seal up the house the best you can. Control filtration if you can. Reduce the amount control ventilation. Reduce the amount of ventilation. And then this is where filtration can really be important. So this is where HEPA air cleaners, right-sized HEPA air cleaners, or good do-it-yourself air cleaners that you can find online become very important, because now you're reducing the amount of ventilation you want, and that can lead to an increase in fine particulate matter levels from indoor sources. When you do that, you're trying to protect yourself from the outdoor environment. At the same time, if you're cooking when you seal up your house and you reduce ventilation, or if somebody has COVID in your home and you don't want to be exposed to the respiratory particles, you need to make sure that you reduce the particle levels to the extent you can using good filtration in your mechanical system, or one or more portable HEPA air cleaners, or do-it-yourself air cleaners. And Stephanie Holm in her presentation did indicate the potentially tremendous health benefits from doing that during wildfires. And that, again, the details are in the actual report.
Excellent. Another question was related to some of the disparities that you talked about between different communities and the different sources they might be exposed to, maybe differences in the housing stock. Could you talk about kind of what's maybe the most important thing? Is there a most important thing for people to do when they have limited resources to take action to reduce their exposure to indoor PM? And also, is there ongoing research that's addressing this gap?
Well, those are great questions. Second one first. I think everybody who spoke, as well as the workshop committee itself, feels like that there are systemic problems in underserved communities, marginalized communities in the United States, that they have a greater exposure to fine particulate matter from sources that matter, that cause health effects, and they're in buildings that exacerbate or magnify those exposures and health effects. And many simply don't have the resources to retrofit their buildings, if they even own the home they're in, which many are not, or to purchase things like portable air cleaners to help themselves. So it's a really complicated problem. It's a systemic problem, and the speakers in the workshop, as well as the workshop committee, feel strongly that we need systemic solutions to these systemic problems, that this is an area where we really should be focusing on the most vulnerable in our nation, because they are impacted much more than others, whether it's during wildfire events or COVID or any other sources of indoor particles that are harmful. So for those individuals that don't have the resources, that's why the do-it-yourself, and I hate to use this term, but I'll use it because this is what people know it by. There's the do-it-yourself air cleaner that people are building. It's called the Corsi Rosenthal box. It was a concept that I came up with about 1.5 years ago, specifically staying up late at night trying to figure out how to help people that didn't have the resources to buy more expensive HEPA air cleaners. So came up with this idea of building your own, literally at 1/4 of the cost of a good HEPA air cleaner, and having that be used to make air cleaning more accessible to some. But even then, spending $60 to build one of these as opposed to $250 or $300 for a good HEPA air cleaner, even $60 is too much for many that, from month to month are trying to figure out how to pay their rent, right? So continuing to try to lower the cost of these do-it-yourself air cleaners is important, but that is one thing that can be done. I know that there are many organizations now that are building those and giving them to those who can't afford good HEPA air cleaners. I've been building them in my garage, and there's a team at University of California, Davis that's getting them to farm worker families in the Central Valley of California, right? So we need to do something to help these underserved communities that are having a hard time dealing with COVID-19 and wildfires and all sorts of other things. The best thing is if they can ventilate when there's indoor sources, to open windows in their residences, to turn on exhaust fans on their range hood, if they even have one, and many do not in these communities. So those are the best things they can do right now to try to avoid certain sources. Don't be smoking inside or burning candles, or especially if there's children indoors, or burning incense. Those are the best things we can do right now for underserved communities, and then to try everything we can as a nation to provide the assistance they need to improve their residential environments, which is where many spend most of their lives. Long-winded answer for this is a frustrating issue, and we all want to help, and we need systemic solutions to what we see as a systemic problem for underserved communities.
Thank you. Yeah, it's definitely a complex issue. Lots to think about there. I think we have time for one last question here. If you could give us a little preview or look forward, kind of how will this information from the workshop series be used to inform the consensus study that's being undertaken on this topic at the National Academies?
Yeah, so the speakers that spoke in the workshop, which was really an all-star cast for the topics that we wanted to cover, they provided a lot of wonderful references to past studies. So that's kind of a primer or a starting point for the committee that's continuing this study. So I would say the workshop primed us with lots of great starting points based upon the presentations. And we're going to go from there to dig much deeper into to all of the literature we can find on indoor fine particulate matter and control strategies for reducing exposure and reducing health impacts. But I think the workshop gave us a great primer starting point.
Excellent. Well, thank you again, Rich, for joining us today. It's been a pleasure having you. This has been a great discussion and a great overview of the workshop proceedings. And thank you also to everyone who joined us online for submitting your questions. I hope we were able to address quite a few of them. I know there are some that we had to combine and leave off in the interest of time, but thank you for your participation today. For future announcements of IAQ science webinars and to learn more about indoor air quality, you can visit epa.gov/IAQ. And thank you, everyone. Enjoy the rest of your day.
Thank you.